Welcome back, Math 3 students. Mr. Eicher here, looking at a Chapter 6 logarithm review for your final exam. If you don't have these notes, you can print them and follow along if you'd like. A main goal in this video, we'll do the first page of these notes, reviewing some essential things we'd like you to know about logarithms. Then in the next video, we'll check out these logarithm ideas and concepts. So first things first, we'd like you to be able to state the domain, range, and end behavior of an exponential function. And I've given you an exponential function y equals 3 raised to the x minus 2. It's called exponential because it has a variable exponent. So let's think about what this graph might look like. We could always start with a table of values, x and y. I'm going to pick a couple values of x, say 0, 1, 2. Maybe 3, and plug those in. So that would be 3 to the 0 minus 2, 3 to the 1 minus 2, 3 to the 2 minus 2, 3 to the third minus 2. So what do we get when we evaluate those? We would get 1 minus 2 is negative 1, 3 minus 2 is 1, 9 minus 2 is 7, and then 27 minus 2 is 25. So a quick sketch so we could think about the end behavior and such, and the domain and range. We have x and y. Maybe I'll have a little scale. 0 comma negative 1 would be 0, negative 1, is right about there. 1 comma 1 is right about there. 2 comma 7, and 3 comma 25. Oh boy, way up there somewhere. Now, it would be nice to know where the asymptote is, and the asymptote is going to be at negative 2. You're going to have a horizontal asymptote. You would know this, that, for instance, if you plugged in, let's say, negative 2, that would be 3 to the negative 2 minus 2, which would be 1/9 minus 2. That's really, really close. That's what, like negative 1 8/9, something like that. So if we go over to negative 2 on the x-axis and go down, we'd be at like right about here, negative 2. So there's going to be a horizontal asymptote at y equals negative 2. So your graph's going to look like this. Like so. Now you don't have to graph on your final exam, but either provided the function like that or providing the graph, maybe we'll give you the graph, you need to be able to state the domain and range and end behavior. So the domain would be all reals. You could put any x gives a y in the function, or every x, visually every x on this axis has a matching coordinate on the blue line, the graph. The range, however, is not all reals. Not every y is represented on this blue function. So we would say y's greater than negative 2, not greater than or equal to, since you don't actually reach negative 2, but y is greater than negative 2. You could also state this in interval notation, which would be negative infinity comma negative 2. If you'd like to state it that way. Either way is fine. And then the end behavior, as x goes to infinity, what does the function do? Well, y also goes to infinity. As x goes this way to positive infinity, the function is going up to positive infinity. It's growing. As x goes the other way, as x goes to negative infinity, what does the function do? Well, as x goes to negative infinity, it looks like the function's getting closer and closer to this value, which is negative 2. And that's basically the definition of a horizontal asymptote, when the end behavior, what number the function is approaching for the as the end behavior goes to positive or negative infinity. So those are the main ideas. If you take Math 4 or pre-calculus in college, Math 4 in high school next year, then you'll be asked lots of questions about domain and range and end behavior and some other things. So we wanted to make sure you were familiar with that and wanted to review that with you. Next, to determine, we'd like you to be able to identify if a function is exponential growth or decay. The main thing that you look for is the base. If the base is greater than 1, then it's exponential growth. If the base is between 1 and 0, then it's exponential decay. And the base is when it's written in this form. The base is what is attached to the exponent. So that's the base b. So we can see here that the base is 2. So this would be exponential growth. And this next one, we could see the base is a quarter, which is between 0 and 1. So this would be exponential decay. Now there are, like, I don't know, situations that if the exponent is a negative exponent, you have to be careful. But we are planning on keeping it more straightforward on the final exam rather than incorporate negative exponents. Next, we'd like you to be able to convert from exponential form to logarithmic form and vice versa. So this first one is in exponential form, and then this one's in log form. So if we were to convert this to logarithmic form, we would say this is log. The base is a of c equals the exponent b. So that's our exponent. The logarithm is an exponent, so it equals the exponent, whereas a is the base. So this is the bacon and eggs, if you remember that phrase. And then if we were to go the other way, log form to exponential form, this f is the base, h is the exponent. So your base would be f, your exponent would be h, and it equals what's in parentheses, g. So this would be our answer, f to the h equals g. Compared to this one, our answer in log form is log base a of c equals b. And using these properties helps you answer questions like the following. Solve a logarithmic equation, log base 4 of 2x plus 1 equals 3. So we want to isolate, and to be able to isolate, we have to deal with this log base 4. To be able to get rid of that log base 4, we do what's called exponentiate. Exponentiate both sides. That means we're going to raise both sides to be exponents with the base of 4. So we're going to have a base of 4 raised to the log base 4 2x plus 1. And that equals base 4 raised to the third. So notice that this whole thing becomes an exponent right here. And this becomes an exponent right here. And the reason why we do that is because when you have a base of 4 with a log base 4, those are inverses. So they cancel, and you're left with just 2x plus 1 equals 4 to the third. And 4 to the third is 48. Let's see, 4 times another 4 is, I guess not, 64, not 48, 64. So we'd get 2x equals 63, so x equals 63 halves. Sometimes you have to be careful of extraneous solutions. If we plug in 63 halves into log base 4, do a quick check here, see if it's extraneous. Log base 4, 2 times 63 over 2 plus 1. Does that equal 3? That's a question mark. This quantity right here, this is all positive, so this is defined. Since positive, it's not extraneous. Not extraneous. So our answer is, circle in red, our answer is 63 halves. Also, we'd like you to be able to use logarithms to solve equations such as this one. So we have 9 raised to the negative x plus 5 equals 100. To be able to solve this, we're going to log both sides. Anytime you have a variable that's up in the exponent like that, to get it down from the exponent, we're going to log both sides. Put a log in front of both numbers, like that. And the benefit of doing that is the exponent now, with log properties, the exponent we can write out in front of the logarithm. So we have negative x plus 5 times log 9 equals log of 100. And then we just do a process of isolating the x. So let's divide both sides by log 9. Log 100 divided by log 9. And then maybe we'll get that number in our calculator. We have log 100 should be 10. Log 100 is 10. Oh, sorry, it's 2. Since 2 tens, yeah, so divided by log 9 is 2.0956. 2.095. 095. That rounds like that. Negative x plus 5. And then we'll subtract 5 from both sides. Subtract 5, so we get negative 2.904041. That's negative x equals that. So x equals positive 2.9041. And then since the domain of an exponential function is all real numbers, you can't get extraneous solutions ever when you have an exponential form like this. It's only when you have a logarithmic form that you have to be careful of extraneous solutions. So it looks like our answer is 2.9. We could always check our answer if I did 9 raised to the negative 2.9041 plus 5. I should get roughly 100, and I do. So that looks like a good correct answer. That was the first page of this document. And in the next video, we'll continue this document. And I'll see you later.